Now we're going to talk about pressure, fluid pressure in particular, and liquid pressure, incompressible liquids, pressure versus depth. Now, gases are actually easier than this because the pressure is constant. For a liquid, if it's flat and it's certain depth underneath the water, for example, it's constant at a constant depth. Pressure changes with depth. For a gas is just the same pressure everywhere inside a cylinder or everywhere inside a container. Pressure is force per unit area, units of Pascal, that's the metric. Um, Pounds per foot squared, that's foot-pound second system or British system. And another commonly used pressure is pounds per square inch. Atmospheric pressure is 101,325 pascals and 14.5 pounds psi. 14.5 psi. Force is equal to pressures. Now we got to do it vector wise because now we're thinking pressure is acting downwards. So this would be in the z-axis direction. And the line of action is through the centroid of this. Pressure may not be constant with respect to x and y. That's why it's listed as a function of x and y, which is why we can't take it outside the integral. It's not a constant. At a given depth, it is constant. And the reason that pressure may vary is because you may have a surface that's not flat, but it might be tilted or curved or something like that. We're going to get into how to handle those situations a little later. So pressure is a function of density of the fluid times the acceleration due to gravity times the depth beneath the surface of the fluid. For water, density is 1,000 kilograms per meter cubed. In the British system, its density times the acceleration due to gravity is 62.4 pounds per foot cubed. And that's for fresh water. For salt water, seawater, it's 64.2 pounds per foot cubed. I used to work in the nuclear shipyard, and so I know the value for seawater. Okay, that's my Star Trek Chekhov gag from the 1980s. Okay, why is this true? Fresh pressure is force per area. That's the weight of the water over it. The weight is rho gz. This is the volume of the water. This is the mass of the water. The volume times density gives us the mass of the water, times g gives us the weight of the water above a certain area. And pressure times area gives us the weight. So just find out what P equals, rho gz, just like we said. Now, so let's look at different situations. This is a situation where the pressure does vary with depth. So you have a loading curve, a load intensity diagram. It's a constant width plate, so we're considering a constant width plate. Width is B. And you figured out how to figure out the centroid, the line of action of a force given this loading diagram. Chapter 4. Go back to Chapter 4, just like Chapter 4.10, as a matter of fact. This is point P is called the center of pressure. And you can look at it in the handouts that I put on Canvas, the back cover of our textbook, review Chapter 4.10, review Chapter 7. It goes through the load, it goes through the moment shear diagrams. Okay, so that's how we solve a problem like this. Now, what if it's curved? It's complicated, but there is a trick. There is a trick. If the plate is constant width, just like before, the plate is constant width, it just has a two-dimensional curve. And we've got loading, the loading direction changes, as well as the intensity, as well as the magnitude. It's normal. It's normal to the surface. The loading is always normal to the curve, and the normal changes as you go through the curve. But we take this and we exchange it for this. We draw a free body diagram. One side of our free body diagram is along the curve. The other side is a horizontal, and the other side is a vertical. The force here, this is one force acting on the vertical surface, and it does change with depth. A constant force, since this surface is flat with respect that it's parallel to the liquid surface, this force is constant. It's just equal to rho gz times the width of the plate. Let's see. Pressure is rho gz, width of the plate is that. And then you also have to take the width, this length. And of course, this is a load intensity. And then the weight of the water. So the third force acting upon the plate is whatever is acting on this surface, whatever is acting on this surface, plus the weight of the water that's inside our free body diagram that we've drawn. Now we've got some relatively simple formulas. The hardest part is going to be this, finding the weight of the surface. Now, if the surface is flat, but it's got a variable shape, well, you just got to do the integrals. You got to take the integral over the area, and the total force is going to be the pressure times dA integrated over the total area. The centroid coordinates are given by x and y prime, and the x-axis is what we're conventionally used to. Y prime is tilted to the surface. So the z-axis is not perpendicular to the y prime axis anymore. This y prime is to just help us analyze this plate. Okay, they define the center of pressure, not the centroid of the plate's area. Understand that. Just want to make sure you get that. Okay. And this one, here we have a 3 meter by 1.5 meter plate and a triangular, it's bolted onto the side of a wall, and it's standing off the hydrostatic pressure. Yeah. Okay, here's all the information you need. So we have a loading curve. It's 2 meters below the surface, so the pressure at that, here's 2 meters, 1,000 acceleration due to gravity, 19.62 kPa. kPa is a common unit that you'll use when you're dealing with pressure. Atmospheric pressure is right around 100 kPa. At the bottom part of the plate, it's given by this. You have the loading diagram. You have the load intensity, which is the width of the plate times the pressure at the top and the pressure at the bottom. From the table, look it up in the table, magnitude of the resultant force, area of the trapezoid, 1/3 times the height times the maximum plus the minimum of the load intensity curves. So that's total area. Um, and the centroid now measured upwards from point B, that's H, here's the H right over here, where the force is acting. Um, okay, here's the load intensity curve. So here's the this is something you look up in the back of the table too. I want to double check that. I don't want to just leave it at that. So let's go double check. Yeah, that this is the formula. It's um, the centroid of a trapezoidal area like this is going to be given by twice the um, 1/3. There's the factor 1/3 out front. Twice the length of the small side, which is 29.43, plus the length of the long side, all divided by the length of the short plus the long, times h. Here's h, the 3 meters here. Crunch the numbers, you get the answer. So use the back of the book, but also the handouts I gave you um, that are on Canvas are also good for this too. Whatever resources, whatever tables you need. I think that's the end of this particular example. Uh, total force, total H. Oh, solution 2. Uh, uh, we can do it just like 4.10, and we should get the same answer. Okay. Now we're going to work on this one in the next video.